Hello and welcome to Diplomatic Derivatives. In today's video, we continue normal subgroups and we talk about theorems on normal subgroups. We have already done two theorems on normal subgroup in the previous video where we have discussed the concept of normal subgroup as well as a few definitions related to proper and improper normal subgroup, simple group, Hamiltonian group, and also did two basic theorems that were also part of the CSS exams past papers. So check that video out. Then we can move forward to the rest of the theorem. So in this video we start with theorem number 3. So let's see what the next theorem is. A subgroup H of a group G is a normal subgroup if and only if each left coset of H is a right coset of H, and hence also if and only if each right coset of H is a left coset of H, which is the basic definition of a normal subgroup. When H is a normal subgroup of G, then the left coset has to be equal to the right coset. Again, as I'm saying, make sure you check out the previous video where we explain the definition. So then you will be able to understand from where are we getting this idea. Okay, so the left coset has to be equal to the right coset. This is the condition. Now we have to prove this condition. Okay. So since we're talking about if and only if, it means that we are going to take both sides. So first we take the first side. We are saying that let's suppose we assume that H is a normal subgroup of G. So we have to reach this condition. Then we will assume this and we reach the first condition. Okay. So let's suppose H is a normal subgroup of G. Then according to theorem 2, so again watch the previous video to see what theorem 2 was. I will give a quick recap here, but to prove theorem number 2 you have to watch the previous video. Now according to theorem number 2, what was the theorem number 2? That when H is a normal subgroup of G, then X inverse was equal to H. This is what we proved. Okay, now what you do is you multiply X on both sides. So X here and X here as well. This X inverse and X will become what? Identity. So you are left with XH, and here you had HX, right? So you got XH is equal to HX. This is what you wanted to get, right? Therefore, when H is a normal subgroup of G, then XH is equal to HX for all X element of G. You prove the first side. Now you take the opposite side. Conversely, let's suppose XH is equal to HX, right? Then for all X element of G, XH inverse, what you do is you take this condition, you multiply. Now in the previous step, what did you do? You multiplied X on both sides, right? Now you multiply X inverse on both sides. So here you get XH inverse, and on this side what do you get? HX inverse. So X and X inverse will become identity. We left with H. So what did you get? You get X inverse is equal to H. Now according to theorem number 2, I forgot to write that statement here. Make sure you write that here. According to theorem number 2, when X inverse is equal to H, then H is a normal subgroup of G, which we proved in theorem number 2. Okay, so according to that, H is a normal subgroup of G. Therefore, when H is a normal subgroup of G, if and only if XH is equal to HX. So you proved both the sides. Okay, so this is the proof for theorem number 3. It's a simple proof and also very important. Theorem number 4. Now this is a bit complicated, so make sure you listen carefully. A subgroup H of a group G is a normal subgroup of G. Basic statement. If and only if the product of two right or left cosets of H in G is again a right or left coset. So basic understanding is that you take two right cosets, take the product, the answer is also a right coset. Okay, or you take two left cosets and the product of those two left coset is also a left coset. This means that the subgroup with which the cosets were formed is a normal subgroup. Okay, now we prove this concept. Let's suppose H is a normal. So since we're talking about if and only if, what you will do, H is, let's suppose we take H is a normal subgroup in the first direction. Okay, we assume that H is a normal subgroup. So when H is a normal subgroup, automatically you know that the condition that X inverse has to be element of H. Remember that. When you are naturally assuming that H is a normal subgroup of G, Then x h x inverse, in case when x is the element of G and small h is element of H, right? So x h x inverse has to be element of H. Okay, then H is a normal subgroup of G. Now what you do, you take two elements from capital G, that is A and B. Now for making a left coset, so we are talking about right cosets now. Okay, you can take any, you can take either right or you can take left. It's all on you. We take a b element of G. So with A you can make one right coset, that is H A. So you multiply A from the right, so you get H A, and when you multiply B from the right you get H B. So H A and H B are the two right cosets. Okay, now according, by looking at the statement, you can understand that you want to prove that the product of H A and H B has to be another right coset, so that will be H A B. Okay, you have to prove this thing now. Okay, now you take one element from HA and you take one element from HB. So in HA you are having H1A type of elements, and HB you can have H2B type of elements. Okay, now this, remember that this H1, from where you're getting this H1? From the subgroup H, right? And this H2 also you're getting from the subgroup H, because from that subgroup only you're making this coset, right? So H1A and H2B are elements of HA and HB respectively. Okay, then what you have to prove, the product. So you multiply these two elements, that is you take H1A and you multiply it with H2B. So this product element, this element that you're getting here, will be element of what? It will belong to HA into HB. Okay, logically. But how can you write H1A H2B? You can, if in what you're doing here in this step, you're basically just adding a bracket in the middle. Okay, so H1A H2B can be written as H1 and A H2 in the bracket and B outside. Okay, now this A H2 can be written as H2A. Just swap A over here and H2 over there, right? Why? Because as a normal subgroup, as H is a normal subgroup of G, it means, what is the condition? That left coset is equal to the right coset, right? So HA will be equal to AH. Since HA is equal to AH, then the element of this will be equal to the element of this. So element AH2 will be equal to H2A, right? According to the concept that left coset has to be equal to the right coset. So you can write AH2 as H2A. So when you write AH2 as H2A, this H1 and H2, we already said they are the part of the subgroup H, right? Because from H you're making the cosets. So H1 H2 can be written as H, right? So you can write H in place of H1 H2 and AB as it is. So basically what you proved is that this HA HB is a subset of this HA B. Okay, so you take two elements from HA and HB, you take the product and you come to the conclusion that HA HB is a subset of HA B. Okay, how did you get that? Because this H1A H2B over here is equal to what? HAB, right? So it means that the element which is inside this thing also belongs to this. So therefore this entire thing is inside this. Okay, so you take the product of these two cosets and you're getting another coset. This is what you are going to prove, but here you see that this thing is inside this. Okay, that is the first statement. Again, for every H element of H, HAB can be written as HAB. This HAB, from where are you getting? HAB, the main coset over here, right? This right coset, the element inside this right coset is what? Small HAB. So this AB can be HAB can be written HA inside and B outside. Now you, in place of HAB, you can write HA into EB. E is identity, so it can be added, right? This is element of what? HA HB. Okay, how? Because HA is element of this HA, and EB, which is identity into B, will be element of this HB. Okay, so it means that HA HB belongs to HA HB, right? Therefore this HAB is a subset of HAHB. Alright, this is what we get from here. We write statement number 2. Now in statement 1 and statement 2, what is common? That HAHB is equal to HAB. This is what we get, because since HAB is inside HAHB and HAHB is also inside HAB, therefore they are equal. So since they are equal, what do we get here? That this coset and this coset, the two right cosets, the product of two right coset is equal to another right coset. Okay, so this is what we have to prove. So we take normal subgroup, H is a normal subgroup, and we prove that the product of two right coset is also a right coset. Okay, next we take the converse. Now we suppose that the two right cosets, the product of two right coset is again a right coset. We suppose this thing. Okay, and we have to prove that H is a normal subgroup of G. Now we take two right cosets. Let's suppose we take those two right cosets as HX and HX inverse. How do you get this? Basically, the right coset means what? This X is element of G, right? So X with the subgroup, you get one right coset. X inverse is also element of G, because X inverse is the inverse of X, right? And according to the group axiom, the inverse exists inside the group, right? So since X inverse is also element of G, then the coset formed with it will be the right coset, right? So HX and HX inverse are two right cosets. According to what we supposed that the product of two right cosets is also right coset. Therefore, the product of HX and HX inverse will also be a right coset, which is HX and HX inverse, right? Now, what is inside HX? X, and what is inside HX inverse? X inverse. So when you make a product of X and X inverse, it means that it will belong to HX and HX inverse. Now to make it easier, we just say that as HX and HX inverse, the product, we can say it as HY. Let's suppose, okay, X and X inverse is E, so E is element of HY. Now what did we get? That identity belongs to this product. Okay, the identity belongs to the product, which is HX HX inverse. All right. Now, but H itself is a right coset of H containing identity, and any two right cosets are either disjoint or identical. Means that according to the definition of cosets, we know that either the two cosets are going to be disjoint, means two right coset or two left coset. Either those two could be disjoint, that there is no single common element, or they are identical. That is that they are totally same, totally equal to each other, right? This is the basic definition of cosets, right? So since we just got that identity belongs to HX HX inverse, it means that identity which is also element of capital H, right? That is the main subgroup. So since identity belongs to H and identity also belongs to HX and HX inverse, therefore they are having a similar element. Now since they have a similar element, that means that they have to be completely identical, because if they don't have if they have a similar element, they have to be identical, otherwise they are disjoint, right? But since a common element exists, it means that all the elements have to be same. This shows that HX and HX inverse is equal to H. Now since HX and HX inverse is equal to H, therefore all the elements of HX and HX inverse will also belong to H. Now what is the element inside HX and HX inverse? From HX we have H1X, from HX inverse we have H2X inverse, right? So this element has to belong to H. Okay, I hope it's clear till this point. Alright, so H1X and H2X inverse belong to capital H according to what I just explained. Alright, now what you do, you multiply with H1 inverse on both sides. What is this H1 inverse? The inverse of H1, right? So you multiply H1 inverse on both sides. So what do you get? This H1 inverse and H1 can be written together. And what is left? X H2 X1 inverse is left, right? This H1 inverse H becomes capital H. How? Since H1 is element of H, we know that. This implies that the inverse of H1 also belongs to H. Now since the inverse of H1 belongs inside H, So the coset formed with h1 inverse and h will also be equal to h, obviously, because it's logical, right? H1 is inside h, so you multiply h1 with h, you're getting h itself. Okay, that's the basic logic. So h1 inverse h will can be written as h. Okay, this h1 inverse and h becomes identity, so it's gone. You're left with x h2 x1 inverse x inverse element of h for all x element of G and h2 element of h. So you are having this basic condition. What is this? This is the condition of a normal subgroup, right? That x h2 x inverse element of h for all h2 element of h. So the condition for a normal subgroup is proven. Therefore, H is a normal subgroup of G. This theorem might look complicated when you first look at it, but once you write it down and try to understand it on your own after getting the basic concept of the theorem, it is very easy. It's not difficult at all. So it's just complicated when you talk about inverse, 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 but it's a very easy theorem, and if it comes in exam, it's like a plus point. So make sure you go through it again and try to understand it, because it's just complicated from the face, but it's very easy as a concept. Okay, so that's all for this video. I hope I tried to make things as clear as possible. I hope I was able to do that. We will be talking about quotient groups in the coming video, so make sure you stay tuned for that video. By then, make sure like, share and subscribe to my channel, and if you have any queries, you can type them down in the comment box below. That's all for this video. Thank you and bye bye.